Hi there, class. It's just me, Mr. Wee. I'm going to go over some content for tomorrow's lab, as well as stuff that's going to be on the test. Essentially, I'm going to relate the book stuff to the stuff you're going to do tomorrow, okay? So I know it's a little bit weird that I'm doing it kind of like in this format, but I think it's the most organic, so I don't have to just do a screencast where I can't do literally hands-on stuff, okay? So here, we're going to watch this video. This is essentially what you guys are going to do tomorrow. You guys kind of have like a Bunsen burner, a fire going. What's going to happen is you're going to dip like a little toothpick or something into like a little bit of like a solution with like different elements, and you're going to put it to fire and see what happens. So here's a sneak peek of what's going to tomorrow's going to look like.
I'm going to observe what color. This is lithium.
Okay, so do you see that person? It kind of just popped in, but that girl had like a little toothpick or something on there with she dipped it in like a little bit of element, in this case is lithium. She puts it to fire. Look at the color that comes out of lithium.
Remember that you want to be descriptive with your colors. Calling this red may not be a good description. You may want to say something about the color.
So let's see if she uses. So this is.
I need to clean my wire real quick.
So I'm not sure which element this is, but this is either lithium, sodium, potassium, calcium, strontium, barium, or copper. So I'm not going to tell you.
Heat it up so it's ready to test.
Okay, so she's going to try another color here.
That is sodium.
That's sodium right there. Okay.
Bright red, orange.
And they're all the same. Okay, I believe that should be strontium. Okay, so anyways, that's what you guys are going to do tomorrow. Why is this happening? Okay, so let me go back really quick and kind of describe what's going on. So let me go to my presentation here. This is what I was supposed to show you on last Tuesday that we met. Okay, so don't pretend that this is like a Bohr model, which isn't the best model, but it still works. A Bohr model of hydrogen right here. And look what's happening, okay? Look at that arrow, okay? And look where the electron was. It was in the first kind of orbit, and then it gets sent to the second orbit. Look, first, okay, second. Okay, so imagine this. This is like when the electron is in the first orbit, it's a normal everyday hydrogen atom. But you see that red arrow coming out? Look what happens. That red arrow is kind of, okay, watch. Arrow comes in the second orbit, then goes back out. Okay, so what's happening is imagine that arrow being fire or energy, okay? We're feeding an element some energy, okay? Look what happens. We feed it energy. We can excite the electron, okay? We can excite the electron. So let's look at a still image. So what happens is I feed, let's say this green thing is a electron, some energy, okay? It gets really excited. It goes up to the next level. It can do that. It can go up to the next kind of energy level of electrons, and then it stays there only for a second, and it goes back down. What happens is when it comes back down, it's got to release the energy that it absorbed, okay? And then what happens is the amount of energy that comes out, okay, depending on how much energy it is, you might see it as a color. Okay, so again, all right, electron was in the first energy level. It gets excited because it absorbs some energy, and it comes back down and shoots out some energy. Look, goes back down, and then look, you see that? Okay, watch. Absorbs energy, comes back down, shoots out energy. Okay, so you might see that depending on how much energy it takes in. Okay, you might see different colors, and every element takes in different amounts of energy, okay? So that goes into what you guys were reading about. So hopefully you guys read the actual chapter, and then I can actually explain it and kind of clarify what you're reading, okay? So remember the different energy that came out? I told you energy comes out. You can have different types of energy. Here's all the different types of energy, okay? This map that you guys saw in your book, okay, right here, these are all different types of energy. You might get energy in terms of radio waves, radar, microwaves, infrared, and some energies you can see. In this case, we can actually see, the human eye can see these colors, okay, or this type of energy in these different colors. We are not able to see the colors here, but we have different kind of detectors to kind of see it and visibly see it, but with our naked eye we can't see these, okay? I've never seen what an x-ray looks like in real life. I just know, if I go to the dentist, right, they're taking x-rays of my teeth, but I can't see the rays, right? Well, colors, right, like different colors I can see all over, right? I can see that type of energy coming at me, okay? So that's a type of energy. Look at these energies though. In fact, if I ask you right now which ones are the strongest, most of you guys should say UV rays, because you guys should be scared of UV rays, sunburns and whatnot. It'll give you skin cancer. X-rays, if you guys go to the dentist, you guys know you guys got to wear those big fat jackets or whatever to kind of protect you away from the X-rays, so it doesn't kill off your cellular structure. And gamma rays, okay? You guys don't want to be near that stuff. That's extremely, extremely dangerous. Okay, so here are like 2 things I want you guys to look at, all right? So these are all different types of energies. And listen to this, okay? That's called the electromagnetic spectrum, okay? The ER for electromagnetic, I'm sorry, the ES for electromagnetic spectrum, okay? It just tells you the different types of energy / light there is in the universe. Okay, so just we're not talking about matter, we're talking about pure energy. These are different types of energies that we know of. Okay, so pay attention to the energy comes out as a wave. Look at how the wave shifts. Okay, radio waves tend, like, look at this. Imagine this is being a wave for a radio wave, and then which is entirely true. And then compare it to the wave of a gamma ray. In fact, actually, let's just look at colors. You can even tell the difference between colors here, because if you go from left to right on this electromagnetic spectrum, okay, you'll notice that there's a certain order, right? And there's certain trends and whatnot. Let's talk about that, okay? So look, it goes from red. When you go from left to right, it goes from red to purple, right? And look at the structure of the wave. It gets kind of smooth, and then it gets really, really crazy at the end, right? Same thing here, from red to violet. Look at the shape of the wave here, okay? Red is going kind of nice and smooth. It's got some nice fat hills, right? But then over here, violet just kind of goes crazy. Like, it's got all these little hills, and it, you know, they're kind of popping up more frequently, right? You see these hills more often, right? Okay, let's talk about that. When you have something that has a big fat hill here, we measure the distance between each hill, and we call that wavelength, okay? So if I had to talk about wavelength, and by the way, wavelength, which is measured in meters, okay? And these are really, really small, right? So these are gonna be small meters. Also known as this is the actual sign, the chemical symbol for wavelength, okay? It tells you the distance, the DIST abbreviation between each wave of energy. Okay, look at the wavelength between for the red right here, red here and here, right? Look at the wavelength between violet. However, it's really short. Okay, so red has if you guys notice here on the left hand side, all the waves have a very, very long wavelength. And as you progress to the right, to the gamma rays, they have really, really short wavelengths, right? However, look, as I go from left to right, check out the shape of the wave in terms of how many times you guys see the hills. How many times you guys see kind of like the waves, like how often they occur, that's called frequency. So red has waves occurring less frequently, so it has a smaller frequency. Violet has a way higher frequency, because look, the waves happen more frequently. Get it? Okay, so if you guys talk about this, it's a frequency. Technically, is a little bit more technical. Frequency, which is measured in this thing called 1/s. Okay, what you do is you talk about how many times you guys see a bunch of little waves, and how many times it occurs over 1 second. So you might see as 1/s or s to the negative first power. Okay, that just tells me how many waves you guys see in 1 second, over 1 second. Okay, so the symbol for this is kind of look like a V. All right, that's called frequency, or that's nu, technically, the Greek letter nu. All right, and what this is the let's see, the number of wave cycles that occur in your energy, your light or energy, in 1 second. That's 1 second, okay? Now, why is this important? Because look, there's a relationship. Whenever you have a long wavelength down here, you have less frequent, or you have a smaller frequency. Look, the wavelengths actually decrease over time. If you look at this, look, 10 to the second power to the 1 to 10 to the negative 2, 10 to the negative 4. If you keep going, the wavelength of all these different types of energies, they decrease. However, look at the frequencies. There's an inverse relationship. As you decrease in wavelength, look what happens to the frequency of how many waves you get. So radio waves have 3 times 10 to the 6 cycles per second. And then look, it keeps increasing. Radar has a higher frequency. Microwaves have a higher frequency. Look at that. They just, as the frequencies increase, look what happens to the wavelength. It decreases. So that's a relationship, okay? I want you guys to know that, all right? So let's use the symbols. As frequency, this is frequency, frequency increases, the wavelength decreases. Again, this is wavelength, this is frequency, okay? And then the opposite happens too. If your frequency decreases, your wavelength increases, all right? So as frequency increases, wavelength decreases. As frequency decreases, so if I go the other way, like frequency, if I go the way in which it goes down, right, the wavelength actually increases as they go down, okay? So why is this important, right? Because look, actually part 2, you're gonna see some calculations with this. Look how much more energy it takes for me to even draw the wave of a guy that has a higher frequency. And look at the guy, look how much less energy it takes for me to even draw the wave and to represent it in terms of red, right? Something like the energy of red, okay? Here's the relationship between energy and frequency. If you have, so let's see, if your energy wave has a frequency that's higher, the amount of energy it will have will be higher. Now look, it kind of makes sense. Radio waves are on the airways because there's not a lot of energy. So when it gets to you, like music, in terms of we transmit it through radio waves, because it's not going to hurt you. It doesn't have that much. It has a small frequency, long wavelength, so it can really get to you really easily, and there's not a lot of energy. It won't hurt you. However, if we go over here, would it make sense to transmit music through gamma rays? No, because gamma rays have such a high frequency, and I told you, the higher the frequency, the higher the energy, okay? That energy can hurt you. It wouldn't make sense to transmit music through gamma rays, or else with that higher frequency and then that high of power, or that high of energy, it's gonna hurt you, okay? So that's the relationship there. And to be honest, okay, I remember UV rays are kind of like, when you guys ever hear UV rays, you guys might think of the color purple, right? The reason why is because ultraviolet, UV, is right next to the color purple. So what does that tell you about the colors? Who has more energy? Okay, red or kind of like almost violet. Violet does. I mean, look, remember, the higher the frequency, look how often these things occur compared to the red here, all right? This guy has a higher frequency. The color violet has a higher frequency, so it packs a little bit more energy. In fact, it's really close to UV rays, okay? Look at red though, however. It goes really slow, so it's not gonna pack that much energy, okay? So what I'm trying to say is your elements are gonna emit different forms or different colors, okay? It's gonna transmit different amounts of energy. So if you see an element that transmits purple, it actually absorbs more energy and shoots out more energy than guys that take in red, okay? And some elements take in energy and they emit it back, but they're gonna take in an amount of energy and emit it back. They might emit back an amount of energy in microwaves, and you're not gonna see it, okay? So some elements will not transmit color, okay? Because they're only releasing a certain amount of energy that you're not gonna be able to see visibly, right? You can't visibly see it in a microwave, okay? So anyways, guys, I hope that helps for tomorrow, okay? So good luck. I will go through a calculation for the homework a little bit later, okay? Peace, guys. Have a good night.